We're in Calc AB.
Yeah, it's Calc BC.
It's Calc, which is basically you take Calc and you break it into 3 pieces. So, well, I don't know if that, but so Calc AB is like the first 2 pieces. Calc BC is the second and third piece. It doesn't. Calc AB lines up with Calc 1 in college. Calc BC lines up with Calc 2 in college, I believe. But it's just kind of a.
But you have to take Calc AB before you take Calc BC.
The really smart geniuses can do it without. I mean, there are teachers that teach BC all in 1 year as the only course. But it's basically you're doing what we've done. And we've kept, I move. And then, well, not necessarily a semester, but then you still have, I think, 2 more units maybe. 2 or 3 more units that you'd have to still teach and get through. So it's for the people that either already have some base knowledge because, their pre-calc went into it more or there's just, So some schools do let their high honors kids go straight into Calc AB. We don't even offer Calc AB here because it's just not, really applicable. So, okay, we are talking about volume, okay? How volume is an application of integration. So, as we look at this, lesson 5 is volumes by cross sections. So, in this lesson, we'll use calculus to find volumes of 3-dimensional shapes where the cross sections are geometric shapes such as squares, triangles, semicircles, rectangles, and such. Finding the formula for the area of the cross-section is the tricky part, but once you figure that out, then just integrate like you've been doing. In general, if cross-sections are perpendicular to the x-axis, solve the equation for y. If cross-sections are perpendicular to the y-axis, solve the equations for x. And that is really so when we talk about the cross-sections, well, you know what? I'll wait till we get there it's not going to make sense right now. Let's review right now. Not necessarily one of your guys' strengths sometimes, but we need to know some basic area formulas. And I'm going to be honest and say these are basic area formulas you should have learned back in, say, middle school. And they should still be in your heads from middle school. There's the problem. Okay? So, a square with side B.
4B.
That's
area. Shoot.
B squared.
There we go.
Let me remind you, we are talking about area. Thanks for getting perimeter out of the way, but I don't need perimeter. So area is B times B, B squared. Yes?
Yes.
Okay. What about this rectangle where it has the length of B, and then what's it say up here? Height of 1/2 B. So that's saying that this side is 1/2 B.
Can you just say B squared over 2?
You could. Yeah. I have it written in my notes as 1/2 B squared, but is it any different than saying B squared over 2? 1/2 B squared or B squared over 2. Okay. What about a semicircle?
Pi B squared. No, 1/2 pi B squared.
Not quite there yet.
1/2 is diameter, so 1/2.
B.
This whole thing
1/4
is
pi
B.
squared.
Yeah, it'd be 1/4.
What's my radius then?
B.
Half of B.
B over 2, half of B, yes? And then this is a semicircle, which it makes sense why we're talking about semicircles when we start talking about the idea of cross sections. So how do we do area of a semicircle?
1/2 pi r squared.
1/2 pi r squared, but r is B over 2, so 1/2 pi, and I'm going to clean this up in a moment if you want to wait for that.
Yeah.
There's your pieces, yes? 1/2 pi r squared. Give me a nice, neat answer.
1/8 pi B squared.
It is. Do we understand the 8? right here, b over 2 squared is going to become b squared over 4 times this 2 is the 8. And then I'm actually going to write it as pi over 8 b squared. But same thing as 1/8 pi b squared, yes? Okay. Isosceles right triangle with base as leg.
1/2 base times height.
Okay.
B squared.
In this case, this is b as base, and what is this?
B.
It is also b because it says isosceles. So 1/2 base height, which interprets to 1/2 b squared, or b squared over 2 if that's your jive. Okay. What about isosceles right triangle with hypotenuse as base?
Would that be the same?
Nope.
No, it's not. Dang it.
Isosceles is only 2 of them make the same side.
2 of them have the same side, but here's the deal. It's these 2 that have the same side, or the same length.
Can you just do 1/2 base times height, but you don't have the, I don't know.
So yeah, here's the deal. Here's my base, then so where's my height?
No, down 45 degrees.
My height is the distance to the top of the triangle that meets the base at a right angle, yes? So we need to know that little lovely piece. Okay.
Well,
The key is to reason this out, okay? So we need to figure out our height here. Do notice this is an isosceles right triangle. Okay. Thoughts on what we know since it's an isosceles right triangle?
that piece H is the same length as
It is. So right here, if we take this and break this up into 1/2 b and 1/2 b, are you with me? That's 1/2 b and that's 1/2 b. Well, because this was an isosceles here, that means these 2 are the same, yes? Well, now we know that these 2 are the same. I'm going to make the hypotenuse the same. So the height and 1/2 base are the same. Whoops, that's not what I was trying to write. So yes, the height is equal to 1/2 base. Okay. So when we set this up, area of a triangle is 1/2 times the base, which is actually b times the height, which is 1/2 b. So yes, as a full area, we are at 1/4 b squared. Okay. Equilateral triangle.
B cubed. Nope. B squared.
No.
Oh.
I don't know.
Because what do we need to know here?
Height.
Height.
We need to know that height there.
I forget
Oh,
you
are
can't
these
choose height and side.
the 30, 60?
Well, an equilateral would be
60.
60, 60, 60, yes. So what's that mean about these guys?
60?
Those are 60s. This 60 got split in half, so these are
30 and 30.
30s.
There we go.
So it is indeed a 2 30, 60, 90s. The base at the bottom, I should have blown this up because I know this is hard to read, but hopefully you're writing as I say it. This base at the bottom is broken into 1/2 b on either side.
So it'd be the same thing as before?
It'd be B.
Oh.
What's our rules for 30, 60, 90?
Square root of 3 over B. Square root of 3B.
Yeah.
Sine or cosine or
That's my last one.
Square root of 3 over 2b.
Okay, so last year in pre-calc, you had the 45, 45, 90, where the legs are each the same, and the hypotenuse is square root of 2 times a leg. Then we had the 30, 60, 90, where the short leg is your kind of your base 1, the hypotenuse is twice the short leg, and the long leg is square root of 3 times the short leg.
Square root of 3 over 2.
So yeah, the last part that Doug was missing there was the over 2. But in order to do H is the long leg, right? It's the one that is opposite the 60. And so it's going to be square root of 3 times the short leg of 1/2 b, which is indeed square root of 3 over 2 times b. Okay? So now,
Square root of 3 over 4b squared.
Right?
yes, I got ready to veto the 4, but I forgot about, yeah. So area of a triangle, 1/2 times the original base, which is base, times the height we just decided to be square root of 3 over 2 times b. Put it all together.
Square root of 3 over 4 b squared.
Square root of 3 over 4 times b squared. Okay. We're getting your brains thinking here, right? We've got to be able to find area. Now, I will say, it seems like you guys could handle triangles and rectangles and even semicircles. It was just getting the, pieces there. So basic shapes, we have to be able to find the area of. The idea here is that when we start talking, this is what it was referring to up above, but cross sections taken perpendicular to the x-axis. So that's kind of like when we were doing upper minus lower, when we were trying to find area between two curves, right? Our pieces, the distance between them was something that was perpendicular to the x-axis, and when it's perpendicular to the x-axis, you're going to work in terms of x. So they're going to be y equals equations, they're going to be solved in terms of x. If the cross sections are perpendicular to the y-axis, so that's more when like we were doing right minus left, then you're going to be working in terms of y. Okay, so similar to what we've talked about previously. Okay. Let's see what we can do with these. Okay.
We're supposed to finish this today.
No way. Nope.
And I was like, I hope that's not the plan.
No. There's way too much here. That first page went fast. It was nice, easy, finding areas. So.
Whoa.
Okay. So let's look at this example. And I made sidebars here a little bit, but find the volume of the solid whose base is bounded by the function y equals square root of x equals 4, and the x-axis. So realizing that's the shaded area, yes? Okay. We've got this. It's labeled here as y equals f of x, but that's y equals square root of x. X equals 4 is a vertical line, x-axis. Now, if we're just finding we can only find the area of this two-dimensional flat piece, right? Volume is a 3D thing. So where the volume comes in is each cross-section taken is a square and is perpendicular to the x-axis. Now, this is something where I struggle insanely to draw this. But the idea is you're going to have squares. Now, and I'll show you where the base of the square goes from here to here, and then the square is standing up. Okay? So the base of the square, this is the base of the square, and it's a vertical thing. And you've got square after square after square after square after square that's making a three-dimensional object. Okay?
So basically what you're saying is we're looking at it from the side, right?
Well, and this is where I can't draw the square. Let me sidebar for a moment. Okay. I found this site this morning while doing some searching on GeoGebra. I can never say it. Now, what I didn't know.
We're gonna call it GeoZebra. Just for fun.
Okay, I don't think I can change. Okay. I don't think I can change the shapes we're using, or the graphs we're using, okay? So, they have, in other words, the base graph.
Oh,
Like ours is square root of x on the other page, right? I don't think,
square root of x.
if I could get rid of that, this would be more accurate, but I don't think I can get rid of that. I didn't know I could even move this.
I don't think so.
Well, what I'd like to do is get rid of that altogether, but I don't know.
Can you just make it equal 0?
Yeah. Bottom slide bar.
I know the slide bars aren't for that.
Well,
I don't know. We're just gonna go with it. Okay, so our shape is the shape on our graph, our flat two-dimensional shape is different. But so this one is using cross sections between these two graphs. Okay, so right here, and I'm gonna pick square because that's what we're working on. There's the idea that the square is standing up, right? Now, keep in mind. Okay, I was trying to go to 2. I went to 6. So the idea is it's square after square after square. How did I move? Okay, I think if I have to figure out how I move this. But here's the idea that the squares are going to be more packed into this. Okay? But it's, when we integrate, it's the idea that we're adding up the area of all these squares. Okay, so it's the area of the area, you're adding up all of these. And as I increase the number of squares, okay, first of all, I can take this all the way to the end, I believe. Well, it's not quite showing it all the way to the end. But the idea is as you increase the number of squares, it turns into just a solid three-dimensional object the more squares we go. Are you seeing how that is there? It doesn't let me move very well sometimes, but okay, so you have that three-dimensional square there. Okay. And it doesn't even, because now here's the deal. If we had two parallel lines and it was just squares, it'd be just like a big long rectangular prism. But because is the length of the base of the square the same each time? No. Right here, it's going to be skinnier than over here when it's bigger. Okay? So this is the idea of cross sections. Now,
Oh my god, no, my eyes are.
okay. Now, that's what it looks like with squares. Okay?
You gonna hit the triangle button?
Well, I don't know. Are we ready for that? Okay, so I took it back to just one square for a moment. Okay.
Oh, absolutely.
So there's a triangle. Okay? There's 10 triangles. So now notice the top of this three-dimensional shape now is going to come up to a point. The more triangles you get. Also notice the triangles in the center are going to be taller, yes? So you're going to have that curve up top. Okay? But this is the idea of what we're looking at. Our job is just to find the area of one shape, so one square, one triangle, whatever it is, and then we're going to integrate.
Oh, okay.
Okay?
At first I thought we were going to
Because integrating, if you're integrating on the interval from 0 to 5, you're adding up all the infinite shapes in there, the infinite squares or the infinite triangles. And then,
So we're turning integration from area to volume.
because we're going to be integrating area. We're going to be integrating area, which is going to take us to volume. Okay? Do we want to see semicircles?
I thought we were going
Okay, there's semicircles. Let me get a few on there. Semicircles are going to do that dome shape there.
It's like an armadillo.
I was gonna say it kind of looks like a rib cage.
Yeah.
It's like an Arkansas speed bump.
I was gonna say fish.
Fish
Yeah.
is fun.
Now, if I could figure out a way to change these, we could actually, like, I don't have a way to change this equation. We could actually, like, graph it and make it ours. I'm just not familiar with GeoGebra at all. So, oh, that's, I don't know. Okay, so, now I discovered you can have squares and you can have them all on one, which is pointless, but we're doing squares. Okay? So this is when we talk about cross sections. A cross section is a square.
So
Okay.
would we be told to integrate our area under the curve into volume?
Finding the volume is a common application
So
of
like
integrals.
we integrate the area under the curve, like we did last time.
You won't be told to go back and do that. You'll be told either to integrate using cross sections, or we'll also talk about disk and washer methods coming up where we revolve around an axis. No, that's next week.
At first I thought you said dish
No.
and washer. I was like, what?
Disk and washer. Now, so what I'm trying to draw and show you is one. Come on. I'm trying to show you one square. How you artistically draw it is up to you. I stink at it.
What do your notes look like?
Okay? My notes are worse than what I have on my other page here. Okay? I mean, I have that here. I guess in my notes I have it angling down this way. I don't have a good way to draw it. Okay?
So is the graph what is laying flat as what we would see like laying on a table? Is the graph laying flat on a table?
like this here?
Yeah.
Yeah.
Okay.
Yeah, that's flat. And then the squares are what are standing up. So like if my hands are squares, square, 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 and they are fitting that flat piece laying on the table.
Like if I was to put like calculators on top of each other.
So basically that line right
Like-
there between the 2 points
No, it'd be like
is like looking down like this.
Here we go.
Yeah.
Here's the visual.
yeah.
This would be
That's what I
like
said.
all of these standing
Yeah.
next to each other.
Yes.
Like if I could
Hey, that kind
put them there, but they wouldn't all be the same length, would they?
No.
They'd have to
You
shrink
could have
or
to,
grow
like, throw some
bigger.
of these in there.
Okay? There we go. That's
get
the
a
best
little-
I could come up with.
I get it a little bit better now.
As I said,
This feels like
okay. Now,
Like bread's about to explode.
in order to do this,
yeah.
we have to talk about the square. I need to know the area. I'm just going to say area of the square. I need to know the area of the square in terms of this. Now, what did we talk about on the other page? Area is what? Area of a square is what?
B squared is back.
It's b squared. Well, I need to do this in terms of x. So, what is the base? How long? Now, long, when I say how long is the base, it's in terms of x. My base starts here at the x-axis, right? Which the x-axis is y equals 0, if you will. And it goes up to
Like,
this curve. Well, right there it goes up to y equals 3. Right here it goes up to y equals 1.5. This curve is what?
Increase.
What is its name?
like equals cube root or square root of x.
Oh.
This was defined to be y equals square root of x. So what is the distance between 0 and square root of x?
Why?
Okay. Think in terms of x's. What is the distance between 0 and square root of x? Okay, let me ask this differently. If I said, what is the distance between 0 and 5, what would you say?
Why?
What is the difference between 0 and 8?
8.
What is the difference between 0 and square root of x?
Square root of x.
Are we there?
Yeah.
So the idea, Okay, the idea is this distance is square root of x, and technically then what is also the height of the square? Also square root of x, yes? Not that that really, well, it matters, but that's also square root of x. So when we say the area is b squared, but we're using b as what? Square root of x. So it's going to end up being x. Okay? So, now, to find volume, you're integrating area. Okay? So like on this last page here, it talks about you're integrating a of x. That's what we're doing. Okay? So we're integrating a of x. We just said the area, and I'm going to write it as square root of x squared. If you want to go ahead and write it as x, that's fine, because I'll simplify it to be that. But I just, for the visual, the area is square root of x squared with respect to x, so dx. Now, I'm using x variables, yes? And we're using x variables because these squares are perpendicular to the x-axis. I need x boundaries. My shape starts over here at 0. Because it says to the line x equals 4, this shape ends at 4. So my boundaries I'm integrating on are 0 to 4.
That's probably not something we can plug in our calculator. Well, no, we can.
Oh yeah, you could. But this is also very simple to integral from 0 to 4. What was the square root of x squared?
X.
This is 4. Yeah, 1.
You have to integrate. 1/2 x squared, evaluated from 4 to 0.
8.
Yeah.
I mean, I can put minus 0 squared here if you want, but you end up with 8. Okay. I don't have any label here. It is volume, right? So it'd be units cubed, cubic units.
I have a question.
Okay.
On the CD or DC for the cross sections, are those just the same as AB? Okay.
Yes, but they're in terms of y because you're working with y variables in that one.
So that's why they chose.
That's why they, instead of using A and B, they use C and D. Yeah. Okay. I guess I did write over here that A ends up equaling X, but okay. Kind of, a little bit.
Better than I thought.
Okay. I mean, the math itself, that's the easy part, the integrate. Like, that's piece of cake. It's getting it set up that you have to work through.
It's the concept.
Okay? And yes, and I learned last year the concept. Oof, it was rough. That's why I had to find something to at least give you some kind of visual. Because me explaining it, I learned, doesn't do anything. Okay. Let's try 2. Find the volume of the solid whose base is a region bounded by the circle x squared plus y squared equals 9, with the cross sections taken perpendicular to the x-axis are isosceles right triangles with the hypotenuse lying on the base of the circle. Okay?
So we need it in respect to that.
Okay? So it did say perpendicular to the x-axis, which, yes, says we're going to be working in terms of x.
So we need to get it to solve the y.
Okay? So we are going to have to solve this fun thing for y. Is Hannah wanting to go ahead and do this? Well,
I'm just trying to say
yeah. No, and that, I mean, we are going to need that here eventually, so.
Y squared equals 9 minus X squared.
So if we're solving for y squared is 9 minus x squared, and y is what?
Y equals square root of 9 minus x squared. Yeah. Plus or minus.
I leaving the gap help you there?
Chris, you can't get the difference in squares.
You're square rooting it.
you're not trying to get the difference in squares.
I mean, I can factor into 3 minus x and 3 plus x, but that doesn't help. I'm square rooting
Oh,
it.
I see.
Okay. Now, while we are oh,
I mean,
okay, we'll pause on that. But while we're talking about this, that y equals plus or minus the square root of 9 minus x squared, what's going on here? The top half is y equals the positive square root of 9 minus x squared, and the bottom half is the negative square root of 9 minus x squared, right? Okay. Now, I'm not sure we're going to exactly need this because I kind of forgot about how this one works, but okay. What are we talking about here?
Isosceles.
Isosceles right triangles,
Hypotenuse.
hypotenuse lying on the base of the circle. So, again, I can't, think about it's perpendicular to the x-axis, so there's my base, right? There's the hypotenuse. The triangle is going to, I don't know, I feel like it should be drawn at an angle here, but it's going to go up, right? So that's a vertical triangle.
What is the base of the circle?
It doesn't say base of the circle, it says hypotenuse line, base of the circle, as in on the circle.
Oh.
Like that.
It's just the base of the circle just being on the bottom of the circle.
Oh.
I don't know.
Okay.
I mean, it's just, I think don't overanalyze base is what I would say here. Just the hypotenuse is laying on the circle. Like what they're trying to express here is that the triangle is this one.
Yeah.
Where the right angle is up in the air and the hypotenuse is on the circle.
Oh.
That's what they're trying to express.
I got it now.
How you say that
I
necessarily,
was trying to figure out where the hypotenuse was. And
Yeah. So this right here is your hypotenuse. That's what they're trying to, understand. Which means it doesn't look like it in my picture at all. I don't, but this right here is
90.
the right angle. I know it doesn't look like it, but
And then those two be congruent.
Just put a not drawn to scale.
yeah, not drawn to scale disclaimer here. Okay. Let's see. With this in mind, okay, how to go. We need, so first of all, what was the area of the triangle according to our other page?
1/4 b squared.
Ended up being 1/4 b squared. Do I want to use that or not? I mean, okay, here's the deal. That's only going to be helpful if you have it memorized. Are you going to memorize those or are you going to come up with them each time? I'll be honest. I probably would come up with them each time. Now, I'm going to take my triangle and I'm going to draw it here because I need a triangle that I can work with. Does that make sense? Here's my right angle. There's my hypotenuse that's laying on the circle. As we look at this, okay, and I didn't talk about this last time, I probably should have, but we talked about the distance on the last one being 0 to the square root of x being square root of x, right? Keeping in mind that square root of x is also equal to y, right? So I'm going to use that more generic that if you're going up here, from 0 to this curve is a distance of y. In other words, whatever the equation is. We'll throw an equation later. Down here, distance from the x-axis to this is also a distance of y. Okay? Now, with that in mind, where does that apply here? This is y and y. Okay? In other words, where this right here in the middle is your the height of the triangle.
Stop it.
what do we decide this height of the triangle is going to be then?
Y.
It's going to end up being the same here, isn't it?
Yes.
Because
Those are.
this goes into two right triangles. This was isosceles, yes? So those were the same. And then, so that makes those hypotenuses the same of the individuals. So we decided these were the same, right?
So these are 45, 45, 90 triangles.
Uh-huh. When it's an isosceles right, it's going to be a 45, 45, 90. Okay? So now as we talk about this area, what do we do? Area is 1/2 times the base. What is the base of this triangle the way I have it written currently?
Y squared.
2y.
2y officially,
Oh.
right?
Times
Times the height, which is
y.
y.
Just use the y. Or
I'm not going to throw that in yet just because it gets too confusing. Yeah, not yet. Well, we have to throw it in at some point. So when you multiply 1/2 times 2y times y, we are at,
Y squared.
okay? So the area of this triangle is y squared. Okay? Now, we're supposed to be working in terms of x, yes? Y was just the easy way to lead us into it. Okay? I mean, yes, we could have talked about this distance up here being the square root of 9 minus x squared. This distance down here being the square root of 9 minus x squared. But it's easier to talk about it in terms of y and fill in what it equals later.
Why did this area not equal the same as the other area?
What are,
This area.
oh, on the previous page?
Yeah.
So because the way this is set up, we're using y. So this distance is 2y, and on that other one, the entire distance across was b.
Oh, okay.
And so there's the difference right there. Okay, so that's, you had the extra 1/2 in there.
Oh, okay.
In other words, my length here is twice as long, and then that also means my height is twice as long in my new one.
Okay.
Okay. Okay. Now, with this in mind, we said area is y squared, right? You want to do this the easy or the difficult way?
Easy.
So y squared equals 9 minus x squared.
Y squared is 9 minus x squared, yes?
Yes.
So which is where I kind of looked at my notes earlier. I was like, oh, hey, guess what? We don't really need that part in this case. Now, sometimes will you? Possibly. Okay? But we're just saying here then the area is equivalent to 9 minus x squared. Okay. Let's get our volume set up here. Volume. We are integrating area. What is my area?
9 minus x squared.
9 minus x squared
Dx.
dx. On what boundaries?
Negative 3.
Negative 3 to 2.
And which negative 3 to 3 am I using?
The x ones.
The x's, the left to right, yes?
Yes.
Now, that's one way to do it. Well, of course there's another way.
Negative 3 to 0 and 0.
Okay, so where are you going with this? Because I'm going to clean that up. What do we know about this figure?
Remember this.
Could you only do negative 3 to 0 and then flip it? What?
Multiply by 2.
Okay,
2
we have-
times the integral bounded 0 to 3.
there we go. That's what I'm looking for.
That's what I was trying to do.
Is it symmetrical?
Okay, so we have two symmetric halves, yes? We don't have to question that. That is a symmetric circle, negative 3 to 3, no question about it. So you can do either of these, okay? It's an either or option. Now, you're integrating the same thing in both times. The advantage of doing the 2 times 0 to 3 is you're going to make less mistakes plugging in 3 and 0 than you would plugging in 3 and negative 3. That's the calculus advantage.
Like accidentally put it in
Huh?
Like accidentally put it in a full.
Well, that's totally different. That's just a weird mistake. But I mean, it's you guys have you guys learned it's pretty easy when 0 is the bottom one, because usually that, not always, but usually you don't even really have to do it. Don't always assume that, right? Occasionally you have to actually plug it in. So that's why I'm going to say either or. Okay. Integrate. What's the integral of 9? Minus integral of x squared.
No.
1/3 x cubed.
1/3.
Gosh, dang it. I forgot to put, if I'm using this one, what did I forget to put out front?
Times 2.
Times 2. And this is going to be how do I want to do that? What? Evaluated from 0 to 3. I know, I'm trying to figure out where I want my 2. I'm confused. That's what I would do. I had a momentary mind blank. Just go with it.
I just know
Yeah, I don't think.
Okay. The idea is the 2 gets multiplied in at the end, right?
Yep.
Plug in 3. Plug in 0.
36 units cubed.
Okay. The argument there is it's so much easier to plug in 0 as a second bound and multiply that answer by 2 as opposed to plugging in 3 and then plugging in -3. You do you, though, right? Obviously, had you done this one, would it come up the same? Barring no mistakes. Exactly, right? So. Okay, so yeah, this is using the idea of symmetry here. Okay. Okay, where are we at? We're about there, aren't we? Will we get done today? Huh. You asked that way too early.
That's a good joke, Kylie.
I'm gonna go out to my car and get some fresh air. It is so cold.
Are you sure?
Okay.
No, I'm freezing. No, you're freezing.
It's down.